Hello and welcome to the video solutions. Today we're detailing problem 1915 in Hibbler's Dynamics book. And so the problem that we're given is basically a tennis racket. So the problem goes, it says here that we're given a 1.25 pound tennis racket with a center of gravity at G and a radius of gyration about G of 0.625 feet. Okay, so we are asked to determine position P where the ball must be hit so that there is no horizontal force exerted by the racket on the hand. Now, to get into the context of this problem, we have a short video to kind of give you an idea of what we're talking about. And as you can see, ball gets hit, there's an impulse type of term that goes from the racket to the ball, and the ball returns to the position that it was coming from. So to start delving into the problem, we first must have a free body diagram. This is an important first step to determine all the forces that are in play with the racket, and to be used to determine the eventual position of RP, which would be the distance away that there is zero force would be exerted on A. So because of that, there's no, as you can see at A, there's no vertical force in the direction of the racket. So we're going to be using an impulse momentum method type of term. So as seen in the video, there's a type of impulse that will be going on in this problem. So we have the terms of L1, which is initial momentum. We have some integral form of a force with respect to time, which is basically an applied impulsive force that we will be studying. And finally, to finish off the conservation of momentum, the final momentum problem. And so, in addition to linear momentum, we also must consider angular momentum as well. And so it's kind of similar, somewhat terms. In this case, we have h1, which is an initial angular momentum, as well as the summation of the integration of the moments with respect to time, that give us finally our final angular momentum. So, just as important as the free body diagram is the kinetic diagram, to essentially portray what equations are going to fit where and what kind of end results from different equations that we're expecting. So as we see with the free body diagram, we at the second plus is we have a kind of a force at P, and then we also have a force as well at A. It's kind of like a resultant force with no horizontal force being applied to A. So this is kind of going to end up resulting in a moment about G with an angular velocity like term, as well as some type of linear velocity term as well. So now moving into the method, we're going to basically, since we know that the racket is starting at rest, we know that both for the linear momentum, the initial linear momentum is 0, as well as we know that the initial angular momentum is 0 as well, as it's not rotating either. And so going along this kind of idea, we can kind of get an idea of both linear and angular at the same time. So as we see here, the integration of the impulsive force with respect to time, we see that the force with respect to time goes to 0 in this problem, but we have some kind of force that's hitting P, such as the ball, when it's being struck by the tennis racket. We also have a summation of the moments with respect to time from T1 to T2, and that's a result of this force at P, basically rotating around A. Now that we know that part, now we finally go to the final state. So we see here with the linear momentum portion, that is simply a relation of the mass times the velocity, which we can relate to an omega-like term of the angular velocity times the radius away. The mass was given to us, 1.25 pounds. Convert that to mass. And we know the radius is 1, as we're given from the problem, as g, where the omega-like term is going around, as we see in our kinetic diagram. And so we were given that distance of 1 foot. And so we see a relation of 0.0388 omega. Likewise, with the angular momentum term, that is the inertia times the omega, which is just m times the radius of gyration squared times omega, and we get an end result of 0.0152 omega. Okay, so before moving to the final step, let's just quickly go over what we've gone through so far. So we were given the problem of a racket, and we need to find the point where the force at P can interact with the racket such that the vertical force at A is equal to 0. So we use the impulse momentum method for both linear and angular. And so the linear impulse momentum, just to review, is basically the initial momentum plus some applied impulsive force term that encapsulates, as it says, applied forces, to end up with a final momentum. Likewise, with angular impulse momentum, we also need that as well, because the racket is also rotating when this force is applied, with A being at rest and the racket moving, as was shown in the video earlier. We need an initial angular momentum term. In this case, ends up being 0. But then we also have an applied impulsive moment, which is going to be due to that force at P, resulting in a final angular momentum term. And this is once again shown in the kinetic diagram. That's also important, relating the free body diagram to relating the kinetic terms to the terms that we have in our free body diagram. So then we went through the method, going through the initial state with the racket at rest. Like I said, both the linear and angular momentum ended up actually being 0 because the racket was not moving relative to the coordinates we're using. We have the summation of the impulsive force, and we found that the force at A ended up being 0, plus the integration of the force at P, which affected T at the time. And then we also had the summation of the integrations of the moment. In this case, the only moment being applied around A was the force due to P, as the force at A is at A, and therefore has no moment arm and can contribute no applied moment. And so, as we went through, we found that relationships between the final linear momentum with respect to the angular velocity. Likewise, with the angular momentum, we found a relationship to the angular velocity as well. So, relating these two, we can see that both sides have an integration of force at P, with the linear side just having an integration of force with P with respect to time, whereas the angular includes the moment arm that force of P is acting at with respect to A. And so when we put these two equations together, solving for R of P, we find that R of P ends up being 1.39 feet. Which, if we go back real quick to our initial diagram, this is greater than 1 foot, which is good, which means it's actually in the racket. This is something that we would expect to be. So we're pretty much sure that is the correct answer to the solution. As we've checked, it makes sense, and we went through the steps. And so we felt it was appropriate to also include another video kind of detailing the end result. Alright, thank you for watching this video solution, and hope that this has made sense for you. Enjoy.